big data stuff. But today I'm going to talk to you, it's the end of the conference, I'm going to talk to you about something I do for fun, which is road cycling. And I'm going to talk about how I was able to use Spark to make road cycling more fun. But first, I want to get a show of hands. How many people in here have an activity tracker or use like fitness apps on your smartphone? Great, great. How about running watches or bike computers? Yeah, so you probably collect a lot of data about things you do every day, both for fun and just as part of your daily routine. But there aren't really a lot of analytic approaches to making sense of fitness data. The focus of my work is on cycling, so I'm going to just give some brief background on what sort of metrics cyclists have at their disposal. I've divided these into 4 categories, and on the top row, we're looking at things that are related to an athlete's effort, and on the bottom row, we're looking at things that are related to the course. And in the left column, we have things that are sort of direct, immediate observations. And in the right column, we have things that are sort of derived or aggregated from these over time, or that lag behind someone's effort. So if you're recording data from a bike ride, you're typically going to have 1 sample per second of each of these metrics that I've circled here. And you're also going to have sampled values for some of these others as well. Now, I want to call out one of these metrics in particular. Power. If you have a power meter on your bike, that measures strain at some point on the bike's drivetrain. And this can really precisely quantify the amount of work that you're doing on your bike at any given time. And so unlike speed, which is affected by a whole host of factors, including wind and drafting, or heart rate, which is a lagging indicator of physiological effort, power gives you a consistent way to pace your efforts and compare efforts across workouts. So cyclists who train and race with power meters know what their historical best efforts are. That is, how much power can I put out on average for 5 minutes or 20 minutes or an hour, and they can use this knowledge to plan workouts. For example, if you were about to get ready for a race and you knew that there was a hill that typically took the field 3 minutes to climb, you could say, well, I'm going to figure out how much power I can put out for 3 minutes, and I'm going to design a workout where I do that much power for 3 minutes, take a break, and then do it again, maybe 5 or 6 times. Power data lets you both pace these efforts appropriately and determine whether or not you're getting better at them, even if you can't train on the exact same course you'll be racing on. So that's just some very quick background before we get into the problem I wanted to solve. Now at Spark Summit, we always see these great applications where people are doing things to keep their best customers happy, detecting fraud, finding diseases. I'm asking a question that's not saving lives or making money. I just want to know where I should do intervals. And for those of you who are in the Bay Area, how many people here are based in the Bay Area? Just a few. This might seem like a silly question, but it's a more interesting question for those of us who can't just find the nearest mountain and ride up it until we get sick of it and then turn around. To show you how this works, here are elevation profiles for 2 bike rides that would take an enthusiastic amateur cyclist about an hour, plus or minus 15 minutes. The axes are to the same scale. So on top we have Mount Diablo, climbing from the North Gate to the summit, just in the East Bay. And then on the bottom we have a hilly time trial course about 10 miles west of Madison, Wisconsin, where I'm based. So we have great road cycling in Wisconsin, but it's hard to pace these steady efforts when you're constantly going up and down these really short, really steep hills. It would be a lot better if you had these steady hills to train on. So my problem this spring, the weather was getting warmer and the thick layer of ice was gradually receding from our roads. I wanted to see where I could go to get consistently high power outputs for longer durations to plan interval workouts. And in the rest of the talk, I'm going to present the 2 analytic approaches that have worked out the best so far, led to the best visualizations, and talk about how Spark made this possible and where I want to go next. The first visualization I want to look at is what I call a power heat map. I started by taking MLlib to cluster points by geographic coordinates from all of my activities, and I used a pretty large number of clusters to get a picture of where I spent my time riding. One interesting but sort of unsurprising thing I found is that it's actually not a very large number of clusters before the cluster centers start really following the roads you ride on the most often. I then analyzed overlapping windows of power samples at different durations that I cared about for workouts to figure out what my best efforts would be at these durations. And the example I'll be looking at in this picture, I was looking for my best 10-minute power. And then finally, in order to see where I was likely to get these best 10-minute efforts, I gave each cluster a value corresponding to how good the best 10-minute effort starting in that cluster was, and I normalized this across all the clusters. I have trouble looking at a map of cluster centers and figuring out what points are actually in that cluster, so I implemented a convex hull implementation on top of Spark, and for those of you who have trouble picturing convex hulls as well, think of it as just putting a rubber band around all the points that are in that cluster. And then I plotted these hulls and shaded them according to the quality of the best effort starting in that cluster. And what that gives us is this picture, which is sort of coarse, but it's still pretty useful, of where I should go geographically around Madison to get really good 10-minute efforts. And each polygon on this map corresponds to a cluster and contains every point from one of my rides over the time period that I analyzed. And the darker polygons are ones in which my very best 10-minute efforts started. So a couple of interesting things about this map is to the west, we have the highest point in southern Wisconsin, which actually has one of the very few sustained climbs that is anywhere near me that I could do leading up to it. So obviously it's easy to get 10-minute effort when you're riding 4 miles at a 6 to 8% grade. And then another one, I'm putting this in here even though it doesn't make me look good. This is a local criterium, very short road race course. And if you're putting out your best power during a road race, you're not riding very efficiently. So I was not riding efficiently when I recorded that effort. Now, maybe we don't want to just see the rough sort of geographic area in which I'm likely to start working hard, but we want to see the actual roads that these efforts are happening on. And this turns out to be a more interesting problem than it might sound just at first. And to see why, we're going to look at a different duration of efforts. We're going to look at 3-minute efforts. So here's an elevation profile of a hill climb time trial course that's very near my house. And as you see, it starts off with a sort of gentle descent where you build up a lot of momentum, and then it goes into 0.8 of a mile at about a 6% grade. So for those of you who are in the Bay Area, you can think of this as sprinting to the bottom of Hawk Hill and then riding halfway up. So I often do repeats on this hill. Doing the whole course takes me under 4.5 minutes most of the time. But the problem is that I'm usually really highly motivated to do well on this workout. And so I've set my best 4-minute and my best 4.5-minute average power here, especially if I have a headwind. But the problem is that a 4-minute all-out effort also includes 60 really good 3-minute efforts, right? And when I went to plot just the best windows of samples, my best 10, my best 20, my best 50 3-minute efforts, I was drawing a picture of this hill. So instead of just finding my 10 best efforts, I thought, well, it would be really more useful to find the 10 best roads on which I had great efforts. Simply plotting the sample windows with the n best efforts won't get us the n best places to work out. But we can use the spatial clustering information we generated before. Since each sample window obviously starts and ends at a given point, we can only consider the best effort starting and ending in a given pair of clusters. And if we do this, we reject most spatially and temporally overlapping efforts. As a consequence, we can find the n best places to do workouts rather than just the n best workouts. And this winds up being a pretty simple query in Spark. After seeing Aaron's talk this afternoon, I think I could make it simpler and faster, but it's just 11 transformations and 2 actions. And I think there is room for optimization, and also it could be simpler in Spark SQL as well. So in this slide, I've plotted the best places to do 1, 3, and 10-minute efforts in green, blue, and red, respectively. And it may be a little hard for those of you in the back of the room to see. I apologize for that. But as a reminder, here are the 2 points I called out on the heat map earlier. Here's that highest point in southern Wisconsin, and there's me to the east racing inefficiently. Another interesting data point on this is the extended double climb from the Wisconsin Ironman Triathlon course. This, as you can see, makes its way into a couple of good 10-minute efforts. Now, these are overlapping efforts that nevertheless start and end in different clusters, but that's still useful information. And then finally, here's that Twin Valley climb that motivated this approach in the first place. So I'd like to talk about why Spark made this possible and where I'd like to take it in the future. We've all heard the sort of promise of big data, that we have smart enough software, we have enough information, we can get insight out of the noise. And we know this isn't always true. right? It's never really that easy. But like Dave said earlier, I was able to use Spark's efficient support for really iteratively refining my analyses until I found something that made sense. And in fact, I've been able to use this to make my free time more productive. Since starting this project, I've used the data to plan workouts and have improved my best 5-minute power by 6% and my best 20-minute power by 7%. So a few years ago, I did some exploratory analysis work on GPS traces of bike rides with no power data in R, and I eventually just gave up because the feedback loop for refining these analyses was just too long. I was waiting around for R for too long. And Spark is not only faster than R, but for some applications, it's even more pleasant to work with. I really like the fact that Scala's type system saves me from making a lot of boneheaded mistakes. So this is a short talk, and it's the end of the conference. I only showed you the analyses that made the coolest pictures. But I've tried a bunch of other approaches to make sense of bike data, and I'm really interested in exploring these some more and improving visualizations and adding some interactivity so that to get insight out of these as well. Another thing I'd like to do is extend this by normalizing data and looking at whole populations of athletes. So you could say not only where are my best workouts, but hey, what are the roads my friends have ridden on when they've really done their best work, and maybe I have never gone on these or heard of them. I could go out there. And then finally, it would be really cool if we could use this as a weight function in an automatic route. So I could give a query to an app like, hey, I want to do 5 really strong 4-minute efforts, but I want to be doing less than 30 miles, right? Or I'd like to leave my house after work, do a 1,700 kilojoule workout and be home before dark, and then get a route back using information based on our historical performances. So I think that's where I'd like to go with this, and I'd like to thank you for being here in the last session, and the 2 links there are to my blog where I have some more detail about this project and to the code for the project itself. I'm happy to take questions now if there's time.
Questions?
Yeah, I'm just curious how much data you actually are collecting and what kind of compute resources you're using to process that data.
So this is a case where it would definitely be more interesting to look at a population of athletes. For my case, the raw data is in the hundreds of megabytes, and it's in the 6 gigabytes or so in memory in Spark once you do all the windowing. But it's on a single 8-core machine.
Sorry. Another question?
So is the power data that you're using basically a proxy for the slope of the road?
Not exactly. The long answer is that you can sort of use as a rough proxy for power data. You can use weight of the athlete, rolling resistance, wind resistance, grade, and acceleration. But power is more accurate because it's actually the amount of work that you're applying to the pedals.
Thanks.
Sure.
It's super interesting, thanks. I'm curious how you actually gathered your data. Did you get it from like a Strava and a basis, or did you develop your own instrumentation? And if it was from multiple sources, did you have to kind of normalize it?
Yeah, so the data is all Garmin TCX files, and it's all collected with the same power meter, but it's with either using a phone app as a head unit or using a Garmin as a head unit. I got a Garmin halfway through this thing because the phone was sort of flaky.
All right, let's give it up for William. Thank you. And so that's the last talk of the conference. If you're returning for training tomorrow, breakfast is at 8, training starts at 9. Thank you.